So we know that the buffer overflow occurs when the data written to a buffer exceeds the memory boundaries of the buffer. So this most commonly occurs when the amount of data written exceeds the buffer's capacity to hold it, and the data is written past the end of the buffer, and if the buffer is allocated in the memory of the program to stack the extra data, overflowing the buffer will override other data that present in the stack. But what does this looks like from the inside the program? So first thing, let's look to function program that shows what it looks like on the program stack. So I hope this picture is becoming familiar to you, because this code and the stack relation is necessary to visualize for understanding a stack buffer overflow. So when we see here, the main function is calling the function 1 and passing to it the name of the program is stored to the argument vector 0 function and the parameter in function 1. So this value is given the function parameter name program function 1, and then it function 1 declares a character array to 16 characters or bytes or length. This local variable is automatically created on the program stack as we can see here in function 1 using the string copy. And copy function, so to copy the name of the program of the buffer and return to the main. So do you see the buffer? Overflow condition that can result if the name of the program is longer than 15 character. So let's visualize it. Let's say the name of the program is my program, and when we run my program, the name of the program is passed to a function 1 which uses a string copy function to copy the name of the buffer, and onto the stack we see that there is a 9 character and the name of the program were copied into the buffer, followed by a null character represented by the \0 0 as the symbol of a C language, and a string character is always terminated with a ASCII or ASCII null character to mark where the string ends. That's the way they did things in the old days of programming. So when you see the C programming was invented, so only 10 of the 16 characters in the buffer were used to store the program name, but on the DOS system the program and the name can include the file extension. So let's try it. We see that the adding the .exe adding the .exe extension, it takes up another 4 characters with 2 characters left over. Now let's say the name of the program file is changed to a something bit longer and bit sillier, like the 16 character buffers then taken by a program name and other than null character. So we're good, but remember about the DOS file extension. Let's try it. So now there is a problem, as you can see right side in the picture. The program name now has overflowed the stack buffer and overwritten function 1 to a function frame pointer, which is not good. Suppose we change the program name to a something even longer, and now the program name has overflowed the buffer. So overflowed that much that for the function it overflowed, So once entire stack frame has been overwritten, and the frame pointer of the frame function as well. Now that we know what a buffer overflow in the stack is and what it does, what it looks like, and what can you do with it, people asked themselves this question many years ago and came up with some interesting answers, like which includes the Morris worm, red code red worm, and many other malware. But for overflows, able to call the system libraries, resident and memory run program that are installed on the local storage system, and even inject and run their own code to the system. And of course, while on the overflow can cause a program to become temporary or permanently unstable and even crash, and most likely program will crash. So the challenge of the buffer overflow exploit to a user of the program as a host to launch a successful exploit before a program crash occur. While fixed virtual memory location makes designing exploit code sound easy, but the location of the exploit code itself and the memory must be predictable to execute the exploit code. The instruction pointer must contain the memory address of the first instruction in the code, and sometimes it is possible to experiment with a vulnerable program in determine exactly where the beginning of the exploit payload might end up in the process memory. So however, the state of the process is execution, which will likely make the contents of the stack not very predictable at that time, but the exploit code is injected, so the code could end up at a wide range of possible locations within the stack to compensate the situation, and the two techniques can be employed to either search for the beginning of the exploit code or restart executing somewhere else. So before it and slide down to it, both those techniques are produce a good results and unpredictable and unguarded execution environment.